This video we will study basic kinetics problem in rectangular components. We will starting first with Newton law of motion, an equation of motion for particles and for a system of particles. And then we will talking about the equation of motion and example uh, for the problem in rectangular coordinate system. Let's start with the Newton law of motion. The motion of particles is governed by Newton's three laws of motion. For the first law, a particle originally at rest or moving in straight line at constant velocity will remain in this state if the resultant force acting on the particle is zero. Or mathematically, we write this equation as summation F is equal to zero. Second law, if the resultant force on the particle is not zero, the particles experience an acceleration in the same direction as the resultant force. This acceleration has a magnitude proportional to the resultant force. Mathematically, for this law, we may write in this form, that is summation F equal to ma. For the third law, mutual force of action and reaction between two particles are equal, opposites, and collinear. So the first and third law were used in developing the concept of static. But for Newton's second law, form the basis of the study of dynamics. That is we will talking about in this topic. Mathematically, Newton's second law of motion can be written as this form, that is F equal to ma, where F is the resultant unbalanced force acting on the particle, and A is the acceleration of the particle. The positive scalar m is called mass of the particle. And Newton's law of gravitational attraction. For any two particles or body have a mutually attractive gravitational force acting between them. Newton postulated the law governing this gravitational force as F equal to the capital G, that is the universal constant of gravitational, that is the value of this constant is equal to 6.673 times 10 power minus 13. That is a very small value. Times m1 and m2 over r squared. M1 and M2 are mass of each body and are represent distance between center of two bodies. And we may find that for any two body, we don't feel anything when we are close to each other because the G, the constant G is very small. Okay, but when we comparison with the Earth, that is a big mass. With some body, we will feel that it has the gravitational acceleration that is become the weight. That is we have a mass, and m1 is maybe the mass of the Earth, and r is maybe the radius of the Earth. So then after we combine, we will get the gravitational constant. That is for mass and weight. Mass is an absolute property of a body. It is independent of the gravitational field in which it is measured. The mass provides a measure of the resistance of a body to a change in velocity, as defined by Newton's second law, by m equal to F over a. And the weight of the body is not absolute, since it depends on the gravitational field in which it is measured. weight is defined as W equal to mg, and g is the acceleration due to gravity. In SI unit, g is equal to 9.81 meter per second square. But in US customary unit, g is 32.2 foot per second square. And we have to know that in SI unit, mass is the base unit. Weight is the derived unit. But in US customary unit, weight is the base unit, but mass is the derived unit. Okay, and weight is typically specified in pounds. Okay, for US customary unit, and it's for the case that the problem is in US customary unit, the problem always given us the weight. So when we solve the equation of motion, we require mass. So then we have to determine mass by weight divided by g. That is, we have to be careful when we solve the problem, as we have to know the unit of weight and mass. So the equation of motion, when we consider the particles, according to the Newton's second law, we can form the equation of motion like this, that is summation F, that is become the resultant force, resultant unbalanced force, that is become equal to MA, that is mass times the acceleration vector. And we can draw the free body diagram on the left hand side and kinetic diagram on the right hand side like this. And the acceleration is in the same directions of the force that we apply to. And if we consider the equation of motion for a system of particles, so for a system of particles, the sum of external force acting on the system of particles is equal to the total mass of the particle times the acceleration of its center of mass g. Okay, so we can use this equation for the system of particles also. So then when we have to solve the problem, okay, the procedure for solving the problem, we may starting with select a convenient initial coordinate system, and then that is we may solve in rectangular components, normal and or tangential components, or cylindrical coordinate. Okay, that is depend on the problem. But for this video, we will focus on the rectangular component first, and after that, in next topic, we will talking about some problem that is the maybe normal and tangential components or cylindrical coordinate system is maybe more convenient for that case. Okay, and after that, we have to draw free body diagram of all external force. This is very important. And then draw the kinetic diagram to show the particle initial force MA. And after that, we resolve this vector into its appropriate components, and it may be depend on the coordinate system that we select. It may be rectangular coordinates, normal and tangential coordinates, or cylindrical coordinate system. And after that, we apply the equation of motion in their scalar component form and solve this equation for the unknown. Okay. And for the acceleration, we may need the proper kinematics relation to generate additional equation to for the equation of motion also for some case. Okay, and one thing that we have to concern is we have to as the first step, we have to set up the initial coordinate system and positive direction. Okay, and we have to use the consistent positive direction. Okay, So then let's we take a look for the rectangular coordinate system. Okay, the equation of motion is defined by F equal to ma. But for rectangular coordinate system, F is decomposed in three components: in X component, Y component, and Z component. That is, we may represent in I, J, and K respectively. Okay, so then for the equation of motion in vector form, that is this equation, this is in vector form, we can decompose it into the scalar one, that is composed of three equations, that is composed of summation fx equal to max, summation fy equal to may, and summation fc equal to mac. Okay, and we will draw the free body diagram, okay, to show all force, okay, and also we form the equation of motion, okay, that is maybe right in vector form or maybe right in scalar equation that's composed of three equations that we mentioned before to provide the direction of velocity and acceleration. Okay, and we have to make sure to use consistent positive coordinate direction when we apply it to equation of motion, that it's a positive sign convention, and free body diagram and kinetic diagram is very important for solving the problem. So let's take a look this problem. Okay, the motor draw in cable with an acceleration AP of 3 meters per second square upward. Determine the reaction at support A and B of the beam. Okay, the beam has a uniform mass of 30 kilogram per meter, and the crate has the mass, the crate C, okay, the crate C has the mass of 200 kilogram. Okay, for this problem, we will not consider the mass of motor. This is the motor and the pulley. Okay, so for this problem, we starting with kinetics of the pulley system first. As we study from the absolute motion analysis between two particles, okay, we can determine the kinematics of the crate and the pulley system. From this picture, we set up the data here, okay, and according to this, we found that we have the point P over here, and then we have SP and SC. Okay, so according to this, we can write the constraint equation that is equal to SC plus SC minus SP. Okay, so then it means that we have this length SC minus SP plus SC. It's become a constant length. Okay, after that we take the derivative both sides. Okay, we can get the relationship of velocity of the plate C and point P. Okay, the second derivative of the constraint equation, we get the acceleration relationship between acceleration of plate C and acceleration of point P. Now, from the problem, we know that acceleration of point P is 3 meters per second square upward. Okay, so if AP is upward, but we set up from this, the datum line is set up at this point, and AP is below the datum, it means that SP is go down as a positive. So then we set up the positive sign convention of go down as a positive. So this means that when we substitute AP into this equation, we substitute, it is become the negative value. because it the problem gives us that it goes up, but the positive direction when it is set up, it is go down as a positive. So then AP is become negative value. So after that, when we substitute into the equation, we found that AC is the negative value also, that is minus 1.5 meter per second square. The negative sign means that the class C will moving up also. Okay, and it makes sense, right? When P moving up, C will also moving up. Okay, but it's move up with the acceleration of 1.5 meter per second square. Okay, this is not equal to AP, that is equal to 3 meter per second square. Now we have the acceleration of crate already. So then we will solve for kinetics of the pulley and the crate. Okay, so for the pulley, we have the free body diagram of the pulley like this. Okay, according to the Newton's second law of motion, we have summation F equal to ma. So then we have the summation F. We is after we set up, we consider the pulley system like this. We have T1 plus T2 minus T1 plus T1 minus T2. Okay, that is equal to mass of pulley times the acceleration of pulley. But because we neglect mass of pulley, so then on the right hand side it becomes 0. So after that we get T2 equal to 2T1. Okay, like this. So then when we consider the crate, okay, for the equation of motion again, summation F equal to m mass of the crate times acceleration of the crate. Okay, but for the kinematic that we already solved, we know that acceleration of the crate now is 1.5 and it's upward. Okay, so for the free body diagram of the crate, we may set up upward as the positive according to the positive direction that we already know. The class C is may go up. Okay, according to the kinematic diagram. Okay, according to the kinematics, the problem that we already know. Okay, crate goes up. So then now for the free body diagram, we set up the upward as a positive. So then for upward as a positive, on the left hand side, summation F is upward is T2. Okay, minus mg. Okay, on the right hand side, which is mc times ac, that is upward as a positive. So according to this, we substitute each value into this equation. T2 is equal to 2T1. Okay, so according to this, we obtain T1 equal to 1131 Newton. So now we already know the tension in the cable that will be connect to the tension from the cable will apply to the beam. Okay, so now we know the tension already, right? And then finally, we consider the beam that is subject to tension T1. Okay, we have 2T1. So from this, we can draw the free body diagram of the beam like this. Okay, that is become the static problem. That is, we have T1, we have 2T1 located in this position. And after that, we would like to find the reaction force By, A1, okay, AX. So we take the moment at point A and then we get By. Go to this. And also after that, we have By. We use summation Fy equal to 0, we get Ay. And after that, when we Consider the summation of x equal to 0. That is, for this case, no horizontal force. It means that ax is become 0. Let's complete this problem.